organizers for the invitation to speak here. This talk will be called An Introduction to Holonomy and G2 Geometry. This talk is meant to be an introduction to the subject for those with no prior experience at all in G2 geometry. In fact, this will be an expository talk. I'm not going to be mentioning my own research whatsoever. However, it is by no means a comprehensive survey. The area of G2 geometry has exploded in the last 10-15 years, and there's so much great work that's been done, but it's impossible for me to mention a lot of it. So in particular, I'm not going to be saying anything about deformation theory. I'm not going to be saying anything about geometric flows. There's just so much important work that I unfortunately won't have time to mention. This is an introduction, a very biased, limited introduction, not a survey. This talk will be in 3 parts. The first part is an introduction to holonomy generally in the Riemannian setting. We'll begin by giving the definition and mentioning the basic properties. Then we'll explain the classification of holonomy groups. In the second part, we'll talk about G2 geometry with an emphasis on G2 holonomy on 7 manifolds. That's going to require some preliminaries from linear algebra. We're going to talk about norm division algebras and the octonions, and we'll use that to discuss G2 structures on 7 manifolds and then explain how G2 structures are related to G2 holonomy. Finally, in the third part, we'll mention some examples of 7 manifolds with G2 holonomy, and just for a little tiny bit, I'll mention some interactions with calibrated geometry and gauge theory. Okay, so let's get started. So let's let M be a connected Riemannian manifold of dimension n. Let gamma be a loop based at a point x. And let's consider P gamma the parallel transport map, where you take a vector v and you parallel translate it along the loop gamma. Now doing this may not result in the vector v that you started with. That is to say, the map P gamma is not necessarily the identity map. However, it is an invertible linear map, and you can consider the set of all such linear maps, P gamma. So let's let the holonomy group of the metric G at the point x be the set of parallel transport maps, P gamma, ranging over all loops gamma at the point x. You can also restrict attention to parallel transport maps where gamma is required to be a null homotopic loop, and this set is called the reduced holonomy group of the manifold at the point x. These sets are in fact groups. They are groups for the same reason that the fundamental group is a group. The group structure is given by loop concatenation. You go around one loop, then you go around the next loop. The inverse of a parallel transport map is what you think it is, just parallel transport in the opposite direction. Parallel translation is an isometry, so the holonomy group is not just a subgroup of the general linear group, but it is in fact a subgroup of the orthogonal group. And in fact, the reduced holonomy group is a subgroup of the special orthogonal group. You might worry that the definition we've given depends on the base point, but it doesn't really. If you have gamma, some path from x to y, then the holonomy group of G at the point y is conjugate to the holonomy group of G at the point x, and the conjugation is given by parallel transport along the path from x to y. So consequently, we can speak of the holonomy group of G and the reduced holonomy group of G without reference to the base point, provided we understand that we're speaking of groups that are defined up to conjugation. Here are some basic properties. The reduced holonomy group of G is connected. It is a normal subgroup of the full holonomy group of G. Notice that if M is simply connected, then all loops are null homotopic, so the reduced holonomy group coincides with the full holonomy group. And in fact, the reduced holonomy group is the identity component of the full holonomy group. A much less trivial fact is that the reduced holonomy group is a closed Lie subgroup of SON. So, taken together, the reduced holonomy group of G is a compact connected Lie group. So the reduced holonomy group of G is a compact connected Lie group. It's contained in SO of TXM. So it has a Lie algebra. Let's call its Lie algebra the holonomy algebra of the Riemannian manifold. Okay, it's contained in little SO of TXM, which we can think of as the set of two forms on the tangent space. So the holonomy group is not just an abstract group. It comes with an additional piece of information, namely it comes with an embedding into SOTXM. To say that another way, it comes with an action, the obvious action, on the tangent space. And so for this reason, the holonomy group is not just an abstract group, it's really better thought of as a representation. And we'll call this the holonomy representation. Okay. So at this point you might ask, why is the holonomy of a Riemannian manifold important? What is this good for? Okay, it's clearly some sort of invariant of the manifold. The reduced holonomy group is telling you about the geometry somehow, and the full holonomy group is telling you about the geometry as well as some pi1, some fundamental group information, but how does it relate to other concepts? And so as we're going to discuss right now, the holonomy is intimately related to curvature, to which tensor fields and which spinor fields are parallel, and it is also related to the presence of extra geometric structure that is compatible with the metric. So let's explore each of these in turn. Okay, how is the holonomy related to the curvature? So for simplicity, let's let T denote the tangent space at a point x. The Riemann curvature tensor is a 4 tensor, but it has various symmetries. For example, if you interchange the first two indices, you get a minus sign. If you interchange the third and fourth indices, you also get a minus sign. You can swap the first two with the third and fourth indices. So the Riemann curvature tensor is not just a 4 tensor, it at a point lies in this specific subspace sim2 of lambda 2 of T star. And in fact, the holonomy algebra constrains the curvature. The Riemann curvature tensor lies in a subspace. It lies in sim2 of Hall G at x, where we're thinking of Hall G at x, the holonomy algebra, as contained in lambda 2 of T star. And so what this means is that the smaller your holonomy group, then the smaller your holonomy algebra, and that means that there are more constraints on the curvature. So the smaller your holonomy group, the more constraints there are on the curvature. So for example, if your holonomy is trivial, then your Riemann curvature is 0 and your metric is flat. A sort of converse to this is given by the Ambrose-Singer theorem. And this says that not only is the holonomy constrained by the curvature, but in fact it is generated by the curvature, in the sense that the holonomy algebra is precisely the subspace spanned by conjugates of the Riemann curvature endomorphisms. So if you know the Riemann curvature endomorphisms, then in principle at least, you could recover the holonomy algebra. In practice, this is not an easy thing to do. The holonomy group also completely controls which tensor fields are parallel, which vector fields are parallel, which differential 1 forms, 2 forms are parallel. All of this is completely determined and determines the holonomy group. This is sometimes called the holonomy principle. So let's let x be a point in the manifold. If you have a parallel tensor field S, then S at a point x is fixed by the holonomy action, or the holonomy representation on the tangent space. And conversely, if you have a tensor at a point that's fixed by the holonomy action, then you could extend your tensor to a parallel tensor field that agrees at the point x with the one you started with. Finally, I should mention that the holonomy group is intimately related to the presence of compatible geometric structure. So the theorem, which is classical, goes like this. Let's say you have a Riemannian n-manifold and you choose a subgroup G of the orthogonal group, then the following two conditions are equivalent. One is that the holonomy of the metric is contained in G, and the other condition is that there exists a G structure on M that is compatible with the metric and torsion-free. And torsion-free means flat to first order. Okay, so in the interest of time, it would take us too far afield to define the terms G structure, G compatible, and torsion-free. So let me just illustrate this theorem with an example that is hopefully familiar from complex geometry. So let's say you have an even-dimensional Riemannian manifold, and let's say you take G to be the unitary group of n over 2, embedded in the orthogonal group in the standard way. A torsion-free U of n over 2 structure, that's just a fancy way of saying Kähler structure. So, which let me remind you, is just a pair G comma J, where G is a metric and J is a parallel, orthogonal, necessarily integrable complex structure. So what the theorem above tells us is that the holonomy of a metric is contained in the unitary group if and only if G underlies a Kähler structure. So in other words, that's equivalent to the existence of a parallel, orthogonal complex structure. So in a certain sense, the smaller your holonomy group, the more geometric structure you get. So hopefully this convinces you that the holonomy group is a very important invariant of a Riemannian manifold, and what you'd like to do, of course, is to classify the holonomy groups, get a complete list of all the possibilities. So to do that, let's first identify two sort of simple cases. So the first case is that of product metrics. So it's an easy fact that if your metric G is a product, then the holonomy group splits as a product. And in fact, moreover, the holonomy action on the tangent space is reducible. So you might wonder if maybe there's some sort of converse to this, and there sort of is. And to explain this converse, let's introduce some terminology. Let's say G, a metric, is globally reducible if it's a product metric. Let's say it's locally reducible if every point in the manifold has a globally reducible neighborhood. And let's say it's irreducible otherwise, so if it's not locally a product. Okay, so this fact above says that if the metric is globally reducible, then the holonomy group is a product of holonomy groups, and the representation is reducible. The converse is given by the so-called Durham decomposition theorem, which says this: suppose your holonomy group at a point is reducible in the sense of representation theory, then there's a local statement which says that the reduced holonomy group is a product group and the metric is locally reducible. And there's also a global statement where if you, in addition, assume that the Riemannian manifold is complete and simply connected, then the holonomy group is a product, not just a product group, but in fact a product of holonomy groups. And the metric G is globally a product. Okay, I've included a more precise statement on this slide. You can hopefully find this in any textbook on Riemannian geometry. I won't read this at you, but this is just a more precise way of saying what it is that I just said. Okay, so that takes care of products. Another special case is that of symmetric spaces. So let's recall that a Riemannian manifold is called locally symmetric if the curvature tensor is parallel. Okay, here nabla is the Levi-Civita connection. Okay, and an equivalent way of saying this is not obvious, but it's equivalent to saying that your manifold is locally isometric to a simply connected Riemannian symmetric space. Now, the simply connected Riemannian symmetric spaces were classified a long time ago by Elie Cartan. There's a complete list of these things. And because there's a complete list of the Riemannian symmetric spaces, and these things are homogeneous spaces, they're very nice, it turns out that you can actually compute very easily, very directly, the holonomy groups of such spaces. So the holonomy groups of simply connected Riemannian symmetric spaces are classified, and consequently the holonomy groups of locally symmetric spaces are classified. So there are two cases in which we definitely know the holonomy group if G is locally a product or if G is locally symmetric. So that leaves all other cases, right? So what happens if G, in the generic case, what if G is not locally a product? What if G is not locally symmetric? Okay, so this is answered mostly by a beautiful theorem of Marcel Berger in 1955, and this is known as Berger's list. Okay, so Berger's list was originally proven by Berger, and then later proofs were given by Jim Simons and I believe Carlos Olmos. Okay, so Berger's list goes like this. Let's say you have a simply connected Riemannian manifold. So because we're in the simply connected setting, we don't have to worry about, the holonomy group is the same thing as the reduced holonomy group. And let's assume we're in the generic setting where G is not locally a product and not locally symmetric. Then the holonomy group of G must be one of these groups, one of these 5 infinite families or 3 exceptional ones. Okay. Now, there's a lot that we should say about this list. Okay, so one thing that has to be said is that Berger simply proved that the holonomy group of G must lie on this list. He didn't actually say that all of these groups are possible. And in fact, at the time, not many of these groups were actually known to occur. I believe maybe the unitary groups and some of the special unitary groups were known. But certainly the groups lower down on the list were not actually known to be the holonomy groups of metrics. And this was an important open question. And in fact, one of the first results was this, proved by Alexievsky and also by Brown and Gray. If the holonomy group is spin 9, then in fact the metric has to be symmetric. So what that means is that the spin 9 case really shouldn't be there. So it's natural to think that maybe G2 and spin 7 don't belong there either. But in fact, it's an amazing thing that all of these groups really do occur as holonomy groups of metrics. It took many decades for mathematicians to prove this. Many people proved over the course of some 30, 35 years that there are in fact metrics, and not just metrics, but complete metrics, and then later metrics on compact manifolds that have these holonomy groups. Some of these metrics are known by other names. As we mentioned before, the holonomy group is contained in a unitary group, if and only if it's Kähler. Maybe you've heard of Calabi-Yau manifolds. Those are precisely the Ricci flat Kähler manifolds, in some definitions anyway. And that's equivalent to the holonomy being contained in the special unitary group. Okay? And the fact that we have compact examples with holonomy equal to SUN over 2 or contained in SUN over 2, that's due to Yau's solution of the Calabi conjecture. Okay. And as we mentioned earlier, the holonomy group is tied up with the curvature. And so the smaller the holonomy group is, the more constraints there are on the curvature. And it's a very beautiful fact that most of these holonomy groups are related to the Ricci curvature. So many of these metrics are Ricci flat. In fact, these are the only known examples. The only compact Ricci flat manifolds that we know have one of these 4 holonomy groups: SUN over 2, SPN over 4, G2, or spin 7. Okay? So in other words, it's an open question as to whether there are compact Ricci flat manifolds with generic holonomy equal to SON. This is unknown. Okay, I should point out that the generic metric has holonomy SON, right? If you pick a metric at random, there's a 99.99% chance that it has holonomy SON, that is the generic case. So it's really quite striking that we don't have any examples of this sort. And if you look at this list, you'll notice that the only odd number that appears outside of the generic case is 7. So in particular, we don't have any examples of a compact Ricci flat irreducible 5 manifold. That's another open question. Okay. So how should we think of this list? There are many ways one can think about this. Here's a way that I like that's somewhat useful. I like to think of these two groups, the unitary and the special unitary group, as somehow corresponding to the geometry is controlled by the complex numbers. The SP groups, manifolds with these holonomy groups are somehow dictated by the quaternions, and G2 and spin 7 are very much tied up with the octonions. Okay, so the remainder of this talk is going to be an exploration of exactly that, G2 holonomy on 7 manifolds. And because of the relationship that we're going to describe between G2 and the octonions, we're going to need to learn a little bit or review a little bit about the octonions, and that will be the subject of the second part of this talk.